we study C19. You can download this PDF file from kpop.org and you visit there to find table of contents, Escape from Scientific Absurdity Series C, and then scroll down to find the C19 here. Okay, so if you click this K-pop lecture K, then you can watch videos. This is Korean version. 오늘은 and English version will be recorded. Is being recorded now, and after that you can click this one to find the English lecture. The download of PDF can be found from this kpop.org. And if you visit there, this one, you can visit the YouTube channel. Okay, so there are many playlists. You can view various subjects. Okay, let's begin. C19, a sphere in an n-dimensional Euclidean space. At the end of this lecture, you will be able to evaluate the surface area and volume of a sphere defined in an n-dimensional Euclidean space. It is not restricted to 2D or 3D. It is a general expression for n dimension. All right. You can click this paper. Let's see. You can click this paper. This paper deals with much more complicated objects defined in the n-dimensional Euclidean and Minkowski space. It will be quite useful if you are more interested in the business and n-dimensional space. Okay. First, we evaluate these two integrals. The first one is a trivial you are familiar with because the derivative of exponential function is itself. The indefinite integral is trivially obtained. We can extend this idea to find out the indefinite integral of exponential lambda x, where lambda is an arbitrary constant. So we can make use of chain rule, use this formula, substitute lambda x for dx given in here. Everywhere it is replaced with the lambda x. We know the total differential of lambda x is a lambda dx because lambda is a constant parameter. As a result, we can integrate both sides, and this one is nothing but e to the lambda x, and we divide both sides by lambda to find the resultant integral table. If we are interested in the definite integral from 0 to infinity, this integral exists only if lambda is negative. Let's see, if I substitute x infinity, we have infinity lambda over lambda subtracted by the one evaluated at x equals to 0. 0 lambda over lambda. This one diverges as if lambda is a positive. So the definite integral exists only if lambda is negative. In that case, this one disappears as x goes to infinity. And this one, regardless of the sign of lambda, exponential 0 lambda is identical to exponential 0, and that is a 1. Therefore, this integral is definite integral is exactly minus 1 over lambda. Then we take the derivative, nth order derivative of this integral for lambda negative by n times. We make use of this to find the integral of this. In principle, you can make use of the integration by parts that derives from the Leibniz rule. But however, it is much more convenient than applying the integration by parts. We begin with this integral we have just derived. If we take the derivative of this with respect to lambda, first order derivative is minus 1 over lambda squared. Second order derivative, so it is 1 over lambda squared. Second order derivative is 2 minus 2 lambda cubed. The next one is plus 2 times 3 lambda to the fourth, and next minus 2, 3, 4 lambda to the fifth. We can find the general expression for this definite integral by making use of mathematical induction. The result is after the first, the second, third, fourth, nth order derivative, nth order derivative. This one is missing in here. Okay, so I have inserted this part. Nth order derivative of this integral is identical to x to the n e to the lambda x. And then mathematical induction can be applied to find a general value. Next, we consider this, a special case when lambda equals minus 1. Then in the denominator is just becomes 1. As a result, we can define n factorial by this integral. We call this n factorial to be gamma n plus 1. Be careful, this n plus 1, and if we write it in terms of factorial, it is n factorial. We'd like to extend this function defined not restricted to an integer, and that was first found by Daniel Bernoulli. This integral show that this gamma alpha is finite for alpha is greater than or equal to 1. Okay, let's see. At alpha equals 1, this one becomes 1, and we have a trivial integral. We know this value is 1. For any alpha that is greater than 1, this integral converges to a certain value. In the limit, as x goes to 0, this factor kills the integrand. So it converges very well. And this factor is a finite, approaches 1 as x approaches 0. On the other hand, as x goes to infinity, this factor diverges. However, whatever power alpha it may be, exponential function kills. Therefore, in both limit as x goes to 0 and as x goes to infinity, the integral converges. By the way, this gamma alpha is divergent as alpha goes to 0. It is equivalent to minus 1 factorial. It is divergent. We recall that 0 factorial, that is equivalent to gamma 1, and that is 1, well defined. That's fine. Okay. Let's see why it is divergent. Gamma 0 can be written in the form. When alpha equals 0, it is a 1 over x. And we have exponential function. This integral can be divided into two pieces, integral over 0 to 1 and 1 to infinity. This part doesn't matter because of this factor, and this one never touches 0 in this region. However, in the limit as x goes to 0, 1 over x diverges logarithmically. Therefore, gamma 0 is not defined. Let's see what happens. 0 to 1, this integral can be divided into two pieces. We know exponential minus x is a sum over k minus x to the k factorial. We single out the first term at k equals to 0, and this one becomes this integral. And the remaining piece runs from k equals 1 to infinity can be written in this form. We can evaluate these every integral. At 0, it's 0, and at x equals 1, the integral becomes k factorial times k. This one, 0 to 1, x to the k minus 1, the x, it is x to the k. And evaluated 0 is 0, evaluated with 1 equals 1 over k. So that's fine. But this one is problematic. This one diverges logarithmically as x goes to 0. Next, we consider gamma epsilon, where epsilon is a fractional number between 0 and 1. So let us exclude 0, both the 0 and 1. If it is the case, we have integrand in here. This is the definition of the gamma function. And we divide this one into two pieces, integral of over 0 to 1 and 1 to infinity. This part represents the convergent integral over 1 to infinity. The integral from 0 to 1 can be expressed by making use of this series expansion. The initial term gives this, and from next on is this. That is already computed as epsilon goes to 0. All right. So we are interested in this integral, and this integral can be evaluated in this manner. Let's see. If epsilon is a positive, then we can find the indefinite integral, that is x to the epsilon divided by epsilon. When I substitute x equals 1, it's a fine. If I substitute x equals 0, because this power is a positive, this term vanishes exactly. Therefore, for any finite number epsilon, 1 over epsilon is a well-defined number. Why don't we extend this idea to compute gamma n plus epsilon, where epsilon is between 0 and 1. We make use of the Leibniz rule to take the total derivative of this factor that appears in the integrand of a gamma function, except that we have a no minus 1 in here. If I take the derivative of this by applying Leibniz rule, we have the differential of the first factor and differential of the second factor. If we simplify this differential is alpha x alpha minus 1 dx, and I copied this factor. This one is a minus exponential minus x dx. I copied this factor. We make use of this relation to find out the integral for the gamma function. Gamma alpha plus 1 is by definition written in this form, and we know this x alpha e to the minus x dx, this one can be moved to the left and rearrange it. This one, this integral, and then this one should be moved to the right to have negative sign on it. This is a total derivative, so integral is a trivial. Evaluated at the indefinite integral is this, and we have to substitute x equals infinity and substitute x equals 0 and subtract them. As x goes to infinity, regardless of the power, exponential kills the integrand. And in the limit, as x goes to 0, it is finite. However, x to the alpha, because alpha is a positive, this one vanishes. So this term is exactly 0. Now we notice that the structure of this second term contains gamma function evaluated alpha instead of alpha plus 1. As a result, we have a recurrence relation just like that appears for the factorial function. Gamma alpha plus 1 is always expressed as a product of alpha and gamma alpha. By applying this relation recursively, I can decrease the argument by 1 by multiplying the same argument in front of the gamma function. We can do this repeatedly, remove this, subtract this argument by 1 more time, and multiply the same factor, And then until we find this minus becomes minus n to cancel this exactly. In that case, the last factor appears in front of the gamma function is epsilon. As a result, this whole thing reproduces this. So once you know the value of gamma function evaluated somewhere around 0 and 1, you can find any kind of gamma function except at exactly the same as 0 that is not defined. This formula is quite useful if I know how to evaluate gamma 1/2, a fractional number that is in this region. I can always compute the gamma function evaluated at an arbitrary half integer such as 3/2, 5/2, and so on in terms of gamma 1/2. We'd like to know how to evaluate this gamma function. So this one is straightforward if you follow the if you can solve this problem 3. Gauss published a definite integral for this, and its value is the square root of pi. We call this Gaussian integral. Why don't you evaluate I squared? First of all, exponential function. This integrand is a positive definite. As a result, this integral must be positive number. We square this integral, then this integral can be parameterized in this manner. We find that this integral can be constructed as a double integral over a two-dimensional Euclidean space. And this is a representation expressed in the Cartesian coordinate system. So we'd like to convert this one in terms of the two-dimensional polar coordinate system. X is r cosine, y equals r sine. We remember in two dimension, this is the Cartesian coordinate representation for the area element. This is the polar coordinate representation of the area element. Because r is a square root x squared plus y squared, this one can be expressed as exponential minus r squared. We move this one to evaluate the radial integral, and we know this angular integral is completely decoupled from the radial integral. It is a trivial. Therefore, this value is this. By the way, I can change the variables to find this. Here, dr, this is 1/2 times 2r dr. This 1/2 times dr squared. Therefore, it is 1/2 times the dt integrated over t from 0 to infinity. Now this integral becomes a trivial. Factor of 2 and factor of 1/2 cancels, and this trivial integral is 1. Therefore, I squared is pi. Then I is plus minus square root of pi. However, we know that this integral is a positive. Therefore, we conclude that Gaussian integral is the square root of pi. Next, we show gamma function evaluated at 1/2 is square root of pi. We make use of the definition of gamma function, gamma alpha equals integral from 0 to infinity e to the minus x dx. We substitute alpha 1/2 for the alpha, then this power becomes minus 1/2. Now we change the variable x equals to t squared, then this integral becomes trivial. First of all, dx equals to 2t dt, and x minus 1/2 is t squared minus 1/2, so that is 1 over t. This 1 over t cancels this t, and we have a factor of 2 multiplied in here. Now, because this integrand is an even function in t, we can convert this one as an integral from minus infinity to the plus infinity. This factor of 2 is absorbed. As a result, because the Gaussian integral is a square root of pi, we conclude that gamma 1/2 is square root of pi. Using this, we can evaluate the gamma function evaluated at any half integer can be expressed in this manner. Next, we multiply the Gaussian integral by n times. If you multiply this integral by n times, we arrive at square root of pi's nth power. That is pi to the 1/2 of n. Now we need to evaluate this. The reason is that we are interested in evaluating the angular integral appearing in the n-dimensional Euclidean space. Okay, now we define the sphere of radius r centered at the origin in the n-dimensional Euclidean space has the Cartesian components n1 through x1 through xn. Because the radius is r, extended the Pythagoras theorem extended to the n-dimensional Euclidean space gives the equation for the spherical surface like that. Now we would like to find the volume element in the n-dimensional Euclidean space using the Cartesian coordinates and polar coordinates. We know the volume of a sphere has the radius dependence of power of n. For example, volume of a sphere in n equals to 3, we know 4 pi third r cubed. This is this. Okay. The volume element should be Rn minus 1 dr. And if we integrate over this, and you will find r to the n and n. And then this 3 appears to be the same. In addition, this is the solid angle that is represented by integral of d omega n for any arbitrary dimension. Now, we evaluate this integral. Why? This volume is reparameterized by the polar coordinates, and radial integral has a volume element this, and this is the angular dependence. Because the integrand does not have angular dependence, we can decouple this angular integral. without knowing the exact value yet. However, this integrand is completely moved to the radial integral, and this is this. Now, we evaluate this integral using gamma function. The result is this. And we change the variable to convert this integral in a form of a gamma function. Now we can determine the solid angle that has been completely factorized against the radial part. We recall that this integral can be evaluated directly by multiplying I, that is the one-dimensional Gaussian integral, by n times. We know the answer. Okay, because we know the answer, we know the answer, this, and we know the radial integral, this. Therefore, we can determine the angular integral, that is this. All right. As a result, I can find the area of the sphere that is the n-dimensional sphere, the area of the sphere of radius r in n-dimensional Euclidean space, radius to the n minus 1 multiplied by solid angle. And the solid angle is evaluated in this manner. Therefore, this is the area. Once I know the solid angle, the volume is a solid angle multiplied by this radial integral. And as I already told you, this is r to the nth power divided by n. As a result, I can copy the omega n here, copy this omega n to find the volume that is simplified in this manner. If you are interested in find out explicit value for the omegas, we are familiar with that for the three-dimensional Euclidean space, that is 4 pi, and we can make use of this table to find the specific values for the volume or surface area of a radius r in n-dimensional Euclidean space. That's it. Thank you.